right. Hello and welcome, everyone. My name is Bruno Janota. I am one of the lead instructors here at Fourth Brain, and I'm joined today with Victor Sanh, who is a lead research engineer at Hugging Face. He's going to talk to you about mastering multimodal models and some of the lessons learned as they were building Idefics2, which is a recently released model, I think 2 months ago, if I'm not mistaken. 8 billion parameter model can do a lot of different tasks and can be easily fine-tuned within the Hugging Face ecosystem. Um, but for those of you that are new to Fourth Brain or haven't engaged with any Fourth Brain events in the past, we run AI workshops across the board. Obviously, a lot of them focused on generative AI and multimodal models. We just did a one-day workshop a few weeks ago on building with multimodal models and integrating them into like RAG workflows. And we have a 3-week workshop coming up, which we'll share the link to in the chat if anyone's interested in building on the type of content you see today and diving into a cohort-based 3-week multimodal workshop. We'll share the link, but without further ado, I'll let Victor introduce himself and share out some slides, and he'll also go into a demo.
Awesome. Thanks, Bruno, for the intro, and thanks for having me. I'm super happy to be here, just sharing about what we've done with Idefics2. So I'm tuning in from literally our New York office based in Brooklyn. You can like see in the back like this gigantic, at least the top of the gigantic Hugging Face. Yeah, so I'm being told this is part of like a longer multimodal focus at Fourth Brain, and so very happy to kind of like deep dive into one of the state-of-the-art multimodal models that we have built here at Hugging Face called Idefics. And yeah, can I share should we dig in? Can I share my slides? Oh, awesome. Cool. So I'm Victor, Hugging Face, been there for like close to 6 years. Done a lot of things, but today I'm going to most specifically to talk about multimodal systems and open access multimodal system. And perhaps just as a general intro, like what is Hugging Face? Hugging Face is the biggest platform for the AI builders today. So data scientists, machine learning scientists, and machine learning engineers are all using Hugging Face one way and another. Hugging Face is this hub where we publish, share public data set, open models, and demos. And people come to this place to essentially use open source data set and models and build their own use case, to do research, to build their own industry production models and all of that. So we have more than 600,000 open source models these days. These numbers are growing like every day. So like it might be slightly outdated. More than 1 million daily downloads through the hub, and all of that is built on top of open source libraries that we develop and maintain. So the biggest, probably the most popular one is called Hugging Face Transformers, that supports tons of transformers, models, and so on. You can fine tune, you can inference, and essentially do research. On top of this library, there's dataset tokenizers, diffusers. Perhaps I'm sure some of you in the audience have used some of these libraries. At Hugging Face, we also do a bunch of open science, like really the core DNA of the organization is to promote and push open science and open source, because we believe it's pushing the community into a more healthy and the AI community in a more healthy place. And so a lot of the team here at Hugging Face is really focused about building very strong artifacts and open sourcing them. So I lead mostly the research on the multimodal side, but others have been working on code, LLMs, for instance, with Star Coder. Others have been working on our LaChef, DPO, like post-training kind of techniques, and so on. And today I wanted to talk more specifically about Idefics, so the work we've done, and I wanted to frame that into the context of what we have been seeing in the past 2 years. So, like, if you're not familiar with ChatGPT at this point, you've probably been living in a cave. So I would just assume that you're very familiar with ChatGPT. ChatGPT came out, what, 2 years ago? A bit more than 2 years ago. And I think it really crystallized a lot of the interest in machine learning and AI towards like the entire tech and general public. Right. So ChatGPT is this large system, large model that take text as an input and outputs text. It has been doing a lot of like post-training techniques, but essentially think of it as an entity, a model that takes text as input and outputs text. There are other examples thinking of Llama 2, Llama 3, much more recently, and we very expected about Llama 3, 400 billion. And in the past 2 years, we've seen also more development towards more modalities. So text to image is a real thing. We have like very, very convincing systems. This day I'm thinking about Stable Diffusion, I'm thinking about DALL-E, but there are other examples that convert a text input to generate a very realistic image, high definition, and so on. More recently, we've seen systems and demos around text to videos, like kind of the same idea. You give a text prompt, and then you can generate videos about dogs playing the snow. That's an example from Sora, but also more recently, Video Poet from Google, with this video from an astronaut riding a horse. And these videos, although they are kind of like very short by everyone's standards, they like maximum a minute long or so. Like it's very impressive the progress that we've done in the past few years. Like it was not possible a few years ago. There's been a lot of interest around audio too, audio to text, with the typical task of translating, transcribing speech to text, but there are other models around music, just noise and things like that. I have perhaps seen this work from Meta very recently, like 2 or 3 weeks ago, from this model named Chameleon that combines image text and also generates arbitrary sequences of image and text. And at this point, I'm sure you've seen the demos of GPT-4o, GPT-4 only, where full modalities are being represented here. Image, text, audio, videos as input, image, text, audio as output. Video, I'm not sure, but like that might be like a stretch here. But it's very impressive. Like we're going towards more and more powerful systems that take more and more multimodal inputs, both on the input side and the output side. And it's very clear that perhaps one day we'll have like all of these modalities on one side, on the input side, and all of these modalities on the output side. Image, text, audio, videos are like the most common one, but we can also think about more funky things like 3D meshes, like biology sequences and things like that. And if you add even more degrees of liberty, you can add language. You can also add embodiment as additional degrees of liberty. Embodiment is this idea that you can put this model into real physical systems like robots that have the ability to interact with the physical world. So it's very clear that a good chunk of the community, including ourselves here at Hugging Face, are really pushing towards this goal, where you have AI systems that can take a lot of different modalities as input, and it outputs a lot of different modalities. And it opens up a tons of different things that we were not able to do like 4 or 5 years ago. I'm thinking, for instance, answering question about documents as the most canonical example that we sometimes see in enterprise, but integrating tons of information from various sources, I think is like a very valuable use case that people have been asking for. So imagination is really the limit here. So very excited to see the systems like coming together and hopefully being opened and unlocking a lot of different use cases. And today, so once I have like given this intro and kind of like framework and context, I wanted to give a presentation that is a little bit different than what usually people give, and kind of really dig into how we build these systems, these multimodal systems, and analyze a lot of the lessons and the mistakes that we did building Idefics. So what is Idefics? Idefics is this open access multimodal language model. It takes image and text as input and output text. And so I gave you here two different examples. So on the left, I'm giving a fake, like a generated, AI generated image of the Pope that the Pope is wearing like this white puffy coat. So it's like, I don't think you can see the Pope like walking around like this. But I'm asking the model, who is in this picture and why do people find it surprising? And the model answers, this person in this picture is Pope Francis, the head of the Catholic Church. People find it surprising because he's wearing a large puffy white coat, which is not a typical attire for the Pope. The coat is quite eye-catching and unusual, which is why it attracts your attention. So it's able like to describe first what's in the image, but also make comments and inference, common sense inference about why people would find it funny, why people would find it surprising and unusual. On the right, I gave this meme of a cat. So perhaps we don't really see really well, but so on the top, this meme says, "I like French people. They eat pain." Yeah. And for the joke, in French, pain is literally pain, which means bread. And so I asked the model to explain this meme to me. The meme features a picture of a grumpy-looking cat with the caption, "I like French people, they eat pain." This is a humorous play on words, as the French word pain means bread in English. But it sounds like it sounds similar to the English word pain, which means suffering or discomfort, and so on. I also asked the model to write a joke based on this meme, and it went on like 3 walks. But French people are walking into a bar, that type of thing. So that's like Idefics 1, and today we're going to dig into the lessons and mistakes from Idefics 1, how we use this lesson to build Idefics 2, and conclude with a short tutorial, hands-on tutorial on to fine-tune Idefics 2 on your own use case. So Idefics 1 started, like the project really started with Flamingo. So perhaps you're familiar with it. It is a model that came out a little bit 18 months ago, maybe 24 months ago, from DeepMind. It was one of the first vision language models, so multimodal model that takes image and text as input and generate text. One of the very first few multimodal systems of this class. And they essentially show in this paper that a lot of the tricks, a lot of the behaviors that we see in pure text language models, we were also seeing them in multimodal systems. And essentially, you could apply a lot of the tricks that we have been tuning, that we have been developing for text in this multimodal context. And so they developed this architecture that they call the Flamingo architecture. That is an architecture that is based on two frozen backbones. So what they did is take a language model backbone, a pre-trained unimodal language backbone, think a Llama 2, think a Chinchilla type of thing. And on the other side, they took a vision encoder. So think of a clip, think of an MAE type of things. So two unimodal pre-trained backbones that have been pre-trained separately on their own modalities, one on language, the other on images, and they're gluing them together to build a multimodal system. And the glue really happens in these gated cross-attentions. So that's like what we see in purple. There's a perceiver resampler module and the gated cross-attention, modules that you see. The details here are not important. We're going to go into details a bit later. But the idea, like, take two pre-trained unimodal backbones, glue them together, and train in a multimodal fashion, essentially. One of the big questions, like once you have talked about architecture, is what type of data are you training on? Where do we find multimodal data? And the answer is, if you want to find multimodal data at scale, you can find it on the internet, right? A lot of the language models are literally trained on a very, very large chunk on the internet, especially through Common Crawl, which is like literally a dump of the internet. And we did the same thing, and Flamingo did the same thing. Essentially, take these dumps from Common Crawl and make them multimodal. People have been just like discarding everything and just keeping the text for the text LLMs. But we can also keep the images and train on this type of documents. I'm calling them multimodal documents. So it's literally a web page as you see it on the browser, on your Chrome, on your Firefox. It's a succession of text paragraph, and sometimes you have images in between these texts. And so on the left, you can see a typical web page that is talking about livestock dogs. And so the paragraph in red, we just shift it on the right. We keep it. And then you have the images, and then you go back to the second paragraph that is highlighted in yellow. So literally, we just take the web page, linearize it, and that's what we call multimodal documents, and that's how we treat it during the training. Web page, treat it as a multimodal document. This gives you an overview of kind of like the whole pipeline of like how we created this massive data set that we call Obelix. So we started from Common Crawl, more than 40 billion documents, and went through a lot of different steps to clean out and to end up with, at the end, 140 million documents and 350 million images. So I think it answers one of the questions in the chat. This is like a massive filtering effort that we've done here. And at a high level, what do these filtering steps involve? They involve discarding a lot of the content that is not grammatical, discarding a lot of the content that is not even rendering, discarding images that are not relevant, discarding not safe for work content, and so on. Essentially, the idea is we want to take raw data from the internet and make it as high quality as possible. Identify the documents, the multimodal documents that are the highest quality as possible. And we end up with more than 100 billion text tokens at the end, which is roughly 140 million web documents. At this scale, it's very, very hard to kind of look at the data and know whether we've done a good job. And I wanted to show kind of a very cool tool that we've used here. It's a tool called Nomic, and I'm just going to switch my switch window. All right. Cool. Okay. So in this map, we are seeing a subset of this massive data set that I just talked about that we built to train these multimodal systems. And what do we see here? Literally every single point is a multimodal document. And so for instance, here we see that some of the documents are talking about books, some of them are talking about Germany, government, COVID, geopolitics. It's a very cool tool essentially to see first at a high level the different topics and the different domains that are being covered in the data set. Perhaps we can go into one of them, for instance. Let's go to presidential election, right? So this one talks about voters.
Hey, Victor, I think on the screen share, we're still seeing the presentation. We're not seeing the Nomic app, like the live view.
How about now?
Now we can see it. Perfect.
Oh, I need to stay on that thing. Okay, I understand now. Okay, sorry about that. All right, so let me just give me 10 seconds. I'm going to do that. Okay, yeah. Okay, cool. I have it side by side. Yeah, so perhaps let's go into a few of them. Yes. So these are reports about car crash. This is COVID, inflation, European politics. So here, you have, I think that's from a news outlet. You have an image, and like here, the article talking about the German federal ministry or whatever. Most of these documents have one or two images. That sometimes at the beginning, sometimes in the middle. It really doesn't matter. But some of them have like as many as 5, 6 images. Yeah. So it's a really cool tool to explore kind of like the data set when you stop sharing the screen. And we learned a few things using the tool essentially. We learned a lot more about the data set itself, like the domain that is being covered, but we also detected content that should have been filtered. So essentially kind of like mistakes and things that we haven't caught in the filtering process. So I think it's a very cool tool to kind of iterate over the data. And because we know that the better quality the data set is, the higher quality the data set is, and the better the models are in general. And so you really want to spend a lot of time looking at the data, understanding where there are patterns, and so on. There's a question, how do we know that the images are related to the text that surrounds it? You don't necessarily know it. And we actually have filters that measure that type of alignment. Historically, I think perhaps let me put that question into the historical context here. Historically, a lot of the image captioning or multimodal systems have been trained on what we call image caption pairs. So it's an image and literally a text description of that same of the same image. So let's say you have like people were eating at the table in an image. The caption would be a dinner at XYZ place or something like that. And so historically, this is the type of data that we've been training multimodal systems on. However, it's very hard to scale them. And it's also discarding a lot of like the content that we actually have at scale on the web and also naturally occurring multimodal documents. And so these multimodal documents don't necessarily have this type of strong alignment. When there's an image that is not necessarily a caption that really describes it very purposefully, I guess. But you can make the assumption that if a document is a coherent role, coherent whole, then if there's an image, the text surrounding it is kind of related to the same topic. And so that's the assumption that we make, and there are filters that measures that in the pipeline I showed just before, to ensure that there's at least an even quality on the time. And the reason why we do that is that experimentally we show that training on these type of multimodal documents instead of just the classical image captions, training on these type of documents yield much better performance on a wide range of different tasks. And so it's important to kind of leverage these multimodal web documents and not just image text caption. Cool. Let's go into really the meat of the presentation. So I'm going to talk, once I've talked about the data set, kind of like the core building block, I want to talk about all the hardships that we have faced while training Idefics1 and how we using these lessons to train Idefics2. Let me paint you a picture. So in classical machine learning, what you want to optimize essentially is to have a lower loss, right? You have an architecture, data, a training objective, and you want to minimize that loss. You want to minimize the error rate. And as the training goes, you want it to go down, right? When the loss or the error is going up, it's usually not a good sign. And that's what happened for us. When we started playing with Idefics2 and we started training, what we see is pictured here. The loss will start to go down, so like fairly normal, fairly standard. It would then plateau or go down very slowly. There isn't much to worry about. It's fairly standard when you train large language models. But at some point, the loss would just diverge and not recover. So divergence in the sense that the loss would spike to infinity or to a very high value, and you would stay at this very high value. If it went down by itself, we would call it a spike and we would just move on. But that's not what we saw. And really, that was a real challenge, like a real mystery. Why would the loss not go down? The even more complicated thing here is that it was diverging like this when training in BF16, but not when we train in FP16. And training in BF16 is kind of like the standard these days because like there are many reasons why BF16 is just better than FP16 these days. So why does this problem happen? Because now we're stuck. We tried a ton of different things to kind of narrow down the problem and probe around the behaviors here. And I listed a few of them. We checked whether there was a data quality issue, so like switch to a higher quality but smaller data sets. Wasn't really that. The funny thing is that when we scaled either of the backbones, whether the text backbone or the vision backbone, it would just, the same behavior would happen just at different times. And the bigger the models we were using and the faster that type of divergence were happening. We tried a bunch of different hyperparameters. We tried unfreezing some of the layers. We're trying some BF16 adaptation and things like that, but we tried a lot of things and none of them were really successful. At least it didn't really unblock us. We did learn a few things. What did we learn? We did learn that we should be tracking activation and gradients. So let's take a step back and look at the transformer architecture. The transformer architecture is essentially a self-attention block and a fully connected layer block, right? And what we're seeing is that At the ends, at the outputs of each of these blocks, we would have activation gradients that grow the fastest, that grow during the training. And so here's some of the plots. You can see it doesn't really matter, but just look at the top plots for now. Whether you're looking at the blue, or the purple, or the green green plot, these are activations. These are gradients that we have been tracking through through the training. It doesn't really matter which metric you're tracking, whether that's L1, whether that's L2, average, median, they would all display the same kind of behavior. And these kind of explosions of activations or even gradients would be a good indication that something is going to go wrong very, very soon. And these explosions would happen right before a training divergence. Now look at the stable run just below. These activation and gradients will not explode during the training. So how do we stabilize the trainings? We went into the literature, and so some other papers that were actually published right when we were having these problems. This is from a paper from a team at Google that analyzed these kind of behaviors. The loss is going down, and then it would diverge and never come back to a normal state. And it happens that a lot of problems happen in the attention module. What happens is that the attention maps would convert to a one-hot, meaning that the model would learn and would emphasize attending to a single token, or just maybe a few tokens in a gigantic sequence. And that would be a characterization of the training divergence. What is a solution that researchers at Google have found? It's very simple. It's applying a layer norm at the right place. So if you're familiar with the transformer architecture, you're probably familiar with the equation on the left, which is the equation where you project the queries, project the project the keys, and then compute the self-attention matrix. And that gives you the attention weights, right? And the only change is to apply layer norms on the queries and layer norms on the keys. So very concretely, that's literally 3 lines of change of code change, just applying a layer norm on the keys and the queries. And that works like magic. To stabilize the training. Funnily enough, this trick has been discovered in the context of vision encoders, vision transformers, but it also works pretty well with text LLMs when they display such type of divergences. So if you need to remember something from these little 2-3 slides, first is to track gradient activations, and layer norms on query key layer normalization is a really effective way to stabilize training in the transformer architecture. Is there a measure, I'm taking a question, is there a measure that tells us when the attention matrix is approaching one hot? Yeah, you can definitely use the entropy the entropy would be a good measure of that. So the entropy measures how much uncertainty is in the softmax distribution. And so depending on which extreme of the entropy you are, it could tell you whether there's a one-hot distribution or there's a uniform distribution. Another learning that is coming from concurrent work is that we can scale the vision encoder further. Remember that you're taking a pre-trained unimodal backbone, the text backbone, glue it with a unimodal pre-trained vision backbone. So the question is like, how do you balance the size of these two backbones? And effectively, what people are doing, and even like the community is doing, is that vision encoders are not big enough. there's this study from Google that showed that you can scale much more the vision encoder and have way better trade-offs in terms of performance for the amount of compute that you're spending because of the increase of size. So that call, actually, that's a good call for training better vision encoders. We don't really have good vision encoders in the open access community. So if I put a lot of these learnings together, we did apply them to train Idefics2, which is an 80 billion parameters multimodal model. And even though we stabilize a lot of the training divergences, some of them still happen at scale when we scale to 80 billion parameters. So here you see on the top and the bottom, you have the loss curve, and on the top you have the learning rate curve that we did. So we trained for 30,000 steps and had to roll back to restart the training for approximately 11 or 12 times. So what does it mean? So whenever we see a spike and it's not really recovering the way we want, we would go back in time slightly, perhaps 100 steps, 200 steps, take a checkpoint, and restart the training from that. Sometimes we had to do that, and sometimes we also had to add a decrease of the learning rate to compensate, to actually stabilize even more. So A, just roll back, B, roll back plus decrease the learning rate to stabilize the training. At scale, that was necessary to do that. When we train a smaller version, a 10 times smaller version, like we did not have to do such contortions to stabilize the training. But that gives you an idea of like the intensity of training such large models. And when you push the button, when you're using so much compute, you really hope that things are going smoothly. They don't necessarily always go smoothly, and so it also implies that we need to monitor trainings whenever they're being launched at this scale. The result of that is that we're matching the performance of Flamingo, which is like the work that we've been replicating through Idefics2. But I don't want to spend too much time on this and emphasize how we are using these learnings to build Idefics2. So Idefics2, 6 months later, and some more learnings later, what did we do? We trained a model that is 10 times smaller, but it is still more competitive than Idefics2. So I just extracted 2 of the benchmark, TextVQA and VQA-V2. And on both of these benchmarks, we have a very strong improvement over Idefics2, even though we're using 10 times less parameters. So Idefics2 is only 8 billion parameters. Idefics2 was 80 billion parameters. So it's much more compute friendly, GPU poor friendly, I like to say. So much more accessible for fine tuning, much more accessible for inference. Yeah. So how did we do that, and what did we learn more here to build Idefics2? The first thing I want to emphasize is around architecture, and I think it's going to answer one of the questions in the chat, is how do we glue these 2 unimodal pre-trained backbones? So on the right, that's literally the Flamingo architecture that we use in Idefics2. So in Idefics2, it's these cross-attention layers that are very similar to what you see in an encoder-decoder. So it's a transformer block that attends. The text is attending to the information from the vision, and you're using transformer cross-attention blocks to do so. And these cross-attention blocks are interleaved in the LLM layers. On the left, you have a much simpler approach that was used in Lava or GIT and other works. And why do I say it's simpler? It's simpler because you take a input sequence. Let's say that in your input sequence, you have an image and a text. The image goes through the vision encoder, and it will generate a sequence of, let's say, 768 vision hidden states. You use these vision hidden states, and you concatenate them with the tokens of the text sequence. And you feed the entire concatenated sequence to the LLM. So there's no cross attention, there's no interleaving. It's just take the vision encoder, encode your images, get a magical concatenated sequence, and feed that to the LLM. So it's a much more simpler architecture. And we try to compare these two architecture. And the main takeaway here is that the cross attention, so the cross attention architecture outperforms the fully autoaggressive, so the easier, the simpler architecture in the frozen backbone setup. So when you freeze the unimodal backbones, the cross attention performs better than the fully autoaggressive, simpler architecture. But freezing these unimodal backbones is somehow dubious choice. Let's try to probe it experimentally. So we try to unfreeze these unimodal backbones. And the funny thing is that now we have the reverse order. The fully autoaggressive, simpler architecture outperforms the cross-attention architecture now. However, what we learn is that you will see some divergences that would appear. It would be hard to train when you need to unfreeze the unimodal backbones. And that perhaps one of the reasons why people have been freezing these unimodal backbones. And one of the way we have found to stabilize the training is to, instead of using full fine-tuning, we're using LoRa fine-tuning. So LoRa fine-tuning is in this type of efficient fine-tunings methods that only fine-tune a very tiny subset or a tiny number of parameters instead of fine-tuning the whole entirety of the model. And experimentally, it can reach the same performance, although recent studies show that there are some trade-offs. So fully autoaggressive, simpler architecture outperforms the cross-attention architecture. That's good because the architecture is simpler, and we like simple things because they scale better in general. So from now on, I'm only talking about the fully autoaggressive architecture. We also learned a little bit more about the unimodal backbones themselves, and learned that scaling the LLM is actually a better use of additional compute than scaling the vision encoder. You have a better increase in performance if you allocate more compute having a bigger LLM than having a bigger vision encoder. Something I'd like to spend a little bit of time on, because I think it's interesting, is image processing. Historically, if you're familiar with computer vision, we've been doing convolutions, and convolutions are great. But the image processing of before getting into these convolutions is a little bit more handcrafted. And historically, we've been resizing images to fixed size squares. So let's say you have an image of 1024 by 1024. Typically, we would resize it to like 378 to 378. Even if the image as input is a rectangle, it would be resized as a square, or would be padded as a square. But that's kind of a weird way to treat images. And for Idefics2, we also included this trick, this improvement that preserves the initial aspect ratio. So if an image is a rectangle, it will be treated as a rectangle. So it preserves aspect ratio, and it preserves resolution. So no need to resize to a smaller resolution. And so a lot of these improvements have been developed in a few papers called Navid and Pixelstruct. Essentially, these are very great tricks that applies the same methods that we've been using in text LLMs to vision LLMs. And the benefit of preserving aspect ratio and preserving resolution is that it's actually much more compute efficient to do so. It reduces the requirements for memory, especially since you don't need to necessarily resize or upsample images. And it doesn't really degrade the performance, like it's the same performance. So you have a much more natural image processing that is on average better at training and inference and reduces the memory cost. So that's great. I'm going to skip that thing, but essentially the idea here is that we don't need necessarily to use the whole sequence of the vision encoder, and we can just pull it into a smaller sequence just for training and inference efficiency here. So if we combine all of these learnings, both from Idefics1 and a few more learnings from Idefics2, we ended up with Idefics2. Idefics is 8 billion parameters. It's better than Idefics1 by a very large margin, and it's improved on a lot of aspects that people really care about, both in the industry and in research. And here I'm showing one example of these capabilities that have been improved, especially on OCR, so the ability to read text that is an image. Here, to be more specific, it's a table. And the table has to do some calculations about some like very simple calculations about the price of something, and counting and doing additions and multiplications and subtractions. And we see, like in the example, like the ability of the model to actually first extract the information from the table and from the image, and then reason over the information, build the different mathematical steps, and bring an answer here. Before we go to kind of like hands-on tutorial, I wanted to highlight a few failure cases of multimodal systems these days. These are true for Idefics1, these are true for Idefics2, but it's also true for other systems like Gemini. And there are a few categories where it's really striking that the systems and the models that we have are making consistent failures and consistent patterns of failures. So I'm giving literally two examples here. So I asked the model to describe an image of Wall-E, and it goes on to describing like the general shape. But I think the main mistake here is that it describes one of the arm as being blue when it's actually not blue at all. Like it hallucinates some details. On the left, it also hallucinates some pots and pans in the back when there is nothing much in the back. So let's dig into some of the failure case, like frequent failure patterns. First round is literally like attributes. So it's saying that it's red when it's yellow, saying that's a dog when it's a cat. So very typical type of failure cases. The second one is describing things that are not here. So is the jam on the bread made of strawberry? It's one example when you can trick the model into thinking, quote unquote, that something is on top of the bread, but it's actually not. And the model here is very happily saying, yes, the jam on the bread is made of strawberry when there's nothing on the bread. So imagining objects or instances that are not here. Comparisons are hard. How do you make physical comparisons between different objects, which is bigger than what, who's on the left of what? Counting is quite hard for the systems that we have today. Is it 2, 3? like 4 apples, 0 apples. Like it's quite a hard task. Hopefully we'll make progress, but I wanted to highlight some of the frequent failure cases of the systems, and none of them really have solved these failure cases here, even the most prominent ones like Gemini or OpenAI. All right, so just like time for practice, I think we have a little bit more than 10 minutes left. So I just wanted to highlight how you can use Idefics2 on your own use case. Now that we have dig into how we built it, like the data set, the architecture, the training stability issues, and so on. How can you use this trained model to fine tune it on your own use case? So I'm going to share. Yes, I'm going to share my screen. How do I switch? Oh, Bruno, can you help me switch? Oh, perfect. Okay, cool. All right. And so this is a Colab tutorial that you'll probably find on the resources online to fine-tune Idefics2 on document VQA. So document VQA is this task where you give a document and like this, for instance, and you ask a question about it. So this is a document from Philip Morris. I think it's from this data set of tobacco industry trials. So there's a lot of text here. I'm not going to read it, but the question I'm asking is which test is used to evaluate RT methods level that has been shipped. And the answer that has been labeled by like humans is a second density test. So that's the kind of task, asking a question about the document that we want to solve here. And so I'm going to go through the core parts of that tutorial and use different techniques to train it in a very efficient way. So we built this tutorial to be accessible with less than 32 gigabytes of GPU memory. So really target for the GPU poor, quote unquote. And like I think that's a great introduction to training these type of models and adapting these models to your own use case. And so here in this block, it's not like crazy science with just loading the model. I'm giving a data set to load, which is a data set of document VQA. We just saw one of the example here. And in the training loop, perhaps that I can stop like for 30 seconds here. What are the inputs of the model? So remember the model takes as inputs images and text, and it outputs text, right? So we need to format the documents in that way. So what are the inputs, how they formatted? So the input IDs are literally the text sequence. The attention mask is which text tokens the model should be attending to. So that's for the text part. And the two other inputs are for the image part. So pixel values, literally the RGB values of the image. And the pixel attention mask is the very same attention mask, which pixels should be the model attending to. So 4 inputs, 2 for the text part, 2 for the image part. That's only what we need to fit to the model. The data collator here is not doing like crazy science. It's just like putting together these 4 type of inputs and making sure that they're the same format that the model expects. It goes through the processor, it computes the labels, and then it trained. I already trained it because it did take a few minutes, like a good 20 minutes, so I didn't have time. And the loss is actually going down, so that's a good sign. It came down from 2.6-ish, and went down to 0.4. but we're only training for 100-ish steps. So we could train for much longer on much more data and so on. Now I want to talk a little bit about evaluation. How do we evaluate this task of document VQA? So remember, you have a question, a document, and extracting the answer from the document, right? And this type of task, this document VQA task, is typically evaluated with what we called a distance metric. So a distance metric compares two strings, two sequences of characters, and this decides how many operations you need to do to transform one string A to a string B. And the closer these two strings are, the lower the distance. Only a few operations as subtraction, as additions to transform string A to string B. And the higher this ANLS score is, so the average normalized Levin-Chance similarity, the higher the similarity and the lower the distance, right? They're just like the opposite of each other. And if you follow that tutorial, we reach essentially a 60-ish, 65-ish ANLS score on that document VQA task. Is far from the state of the art. The state of the art on document VQA is more like closer like to 85, 90 points. But it gives you a very strong introduction with a very, very low budget, compute budget on how you can fine tune the model on your own use case. Awesome, cool. So let's close that hands-on tutorial. And that actually concludes like the content that I had. And I would be happy to take a few questions. I see that some of them have been already highlighted. Okay, in what order should we take them?
Yeah, that's a good question. So I think we have time for one or two questions. You did answer a couple of them prior. I guess one of the questions is, have you and your team had a chance to work much on fine-tuning Idefics to particular tasks, so like task-adapted models? And if so, like any rule of thumb on how much data would be useful? I think it's similar to the question from Marzan Consulting, and I think there was an earlier one um, from Ralph where he asked about kind of how much training data you might need to adapt these models to a new purpose.
Yeah, that's a great question. To be fair, I don't have a general answer to that question, but I can give a few pointers, a few elements of context to ground the discussion here. The first thing I would say is that to train Idefics, we have trained on a bunch of task-oriented data. So that includes document VQA, that includes OCR, that includes image captioning, reading from tables and things like that. So a large variety of different task-oriented data sets. And so as a general rule of thumb, like the closer the task that you're training on, the closer it is to what has already been trained on, and the fewer samples you need, right? So if you are just literally adapting a model for image captioning, which has already been present in the training of Idefics, you probably won't need tons and tons of data. But if you're training, trying to solve a completely different use case, then perhaps like you'll need a lot more. Like a rule of thumb that have been using in guiding people is that there are tons of papers that show that with 1,000-ish samples, highly curated 1,000-ish samples, you can get away and really bootstrap your use case here.
Yeah, I
So
figured the
it's
metric
really
from
experimental,
yeah
but like,
the Lima paper, the less is more for alignment. I think that they said 500 to 1,000 high quality samples, can actually have meaningful impact on downstream model predictions or behavior. So yeah, it sounds like if you're in, if you're in the domain of tasks where it's already quite performant, less data is maybe necessary. But if you're getting into the realm of, you know, detailed captioning, for example, with complex tasks like counting and, identifying orientation of people and all that stuff like that, that might get to into the realm of more curated data. It might be necessary to perform well on that task.
Yep.
Cool. Um, I'll see if we have time for maybe just one more question. Um, yeah, I guess as you made the shift from uh, Flamingo to the Lava, the autoregressive framework, um, I guess is that only applicable? I guess is that most applicable? I guess on the pre-training side, or have you seen any like are there any other like tangible, like obviously you had a smaller model perform better, so like there's maybe some inference upside to using the Lava training approach, but um, I guess were there any other kind of like net benefits of the Lava approach and the Git approach versus the Flamingo model? And have you seen any other emerging architectures that you think might be interesting to experiment with beyond the autoregressive approach?
Yeah, I would separate this question into two parts, like the really scientific / performance part and more like the engineering part. So on the scientific performance part, like it's pretty clear the performance is just better. And like, yeah, like you want to use like the model that is just performing, right? On the engineering part, there's definitely some upside. It's less compute intense. It doesn't requires as much parameters, and which means that it's also faster at training and slightly faster at inference too. But the real core benefit here, I would say, is that this is much simpler and much closer to like the standard LLM, which means that a lot of the tricks, not tricks, but optimization that we've been developing the past few years can be used out of the box. I'm talking about flash attention, I'm talking about quantization, I'm talking about all these like set of tools that we've been developing in the past few years to really make transformers top of the game in terms of inference. These can be applied much more easily to the fully autoregressive architecture.
Awesome. Yeah, I guess just to close out, I know we're over time, so you might have something to back up to, but I guess what are you excited over the next 6 months? Anything that you're looking forward to from a Hugging Face perspective, or just following closely in the broader multimodal world?
I think the multimodal like community is really coming together. People are excited about audio, people are excited about videos and like the potential to unlock. I think one of the biggest challenge in that space really to unlock the next generation of models is around data and data availability. And so we know now that like if you want to train really good models, you need high quality, high volume, high diversity data. And that's really where I think a lot of the work should be focusing on. I think it's like the highest leverage work you can actually do these days. Really work on data.
All right. Awesome. Well, yeah, we really appreciate you taking the time to work with our audience here and share all the lessons learned on building Idefics2. And I know we shared the links here, so if anybody's interested in playing around with it, there's lots of great resources in the blog post and the collection. But yeah, really appreciate your time, Victor, and thanks again for taking the time out of your day to talk to us about multimodal models.
Thanks so much for having me. Really had fun doing that.
Awesome. Yeah, feel free to connect with Victor on LinkedIn or Twitter, and I'm sure he'll be sharing more stuff as they keep rolling it out. All right. Thanks, everyone.
Bye bye.